Hi everyone. We are back with episode 2, which is 2D kinematic equations. The last episode we covered 1D kinematic equations. This episode we're going to really get into circles. Circles and circular motion is the big theme here, and the other part of it is vectors. So there's like 3 things in one we're going to be learning, like a trinity. We're going to learn circles, vectors, and physics. That's my interpretation of doing these problems. Now, whenever acceleration is the key to these kinematic equations problems, it seems to be the concept. Because if we have a constant acceleration, we use these 4 kinematic equations. Remember what I told you, what you're looking for? The V final, X final, X final, V final. No distance, no acceleration, no final speed, no time. And I showed you what to do to not use the vectors with the bases, and the concept with the sign change. And I showed you the first 2 are linear and the second 2 are non-linear. It's interesting too because the third one's almost linear as far as the time. So that's if the acceleration is constant. Now, whenever we travel in the x direction, acceleration can vary. It's not always an exact amount. I mean, it can always change depending upon the situation of the problem, but it's a fixed value. So it's kind of the same thing with, well, we'll get into that later, but it's sort of the same thing. Imagine the second kinematic equation. I mean, this is like the same thing as special theory of relativity. I mean, if you think about it, it doesn't have acceleration. It's kind of like the second kinematic equation, which we're going to cover at the end. That isn't the 4th thing we're going to learn that's actually part of the trinity. This is a trio, is how I'm going to do this episode. If you have an instantaneous velocity, right? We use, well, actually, if we take an average velocity, we just need the 2 endpoints. Instantaneous, we just take the limit as the change of time approaches 0. A change of x over the change of time, which is the dx dt derivative. The average acceleration is the 2 endpoints, the same thing. It's the same as, except for the numerator part. Instantaneous acceleration. And these are if you want the instantaneous accelerations and instantaneous velocities. Basically, the instantaneous means that the initial velocity is set equal to 0. So you only have a final speed value, which you could turn these equations, if you're clever enough. If you're just looking, imagine that V initial is 0, right? That would make this problem instantaneous. It would have an instantaneous velocity. You could argue with the same thing here. You can make this instantaneous if you wanted to, saying that set the initial speed to 0. The third one, you probably wouldn't want to mess with that. I mean, you could if you want. It does have acceleration in there, but you could possibly use it. It's a little tricky because it's quadratic formula. Other than that, let me show you what this collapsation reminds me of. It's not really a collapsation. It's just that the differential and the upper bound limit, they cancel. We call this the FTC, which stands for Fundamental Theorem. Imagine a little of calculus. It's an abbreviation. It's an acronym. Okay, so that is the FTC. Now, this collapsation reminds me of something peculiar. It reminds me of the Copenhagen interpretation, which shows you that if you have a graph, right? You got like a Witch-of-Agnesi kind of function, a wave function versus position before measurement. After measurement, it collapses and has an initial position. So it says before measurement observed at x initial collapse position. This is known as the Copenhagen interpretation, which you can't really find this on the internet, but the real definition is that a system collapses after upon measurement, which is peculiar. It's interesting. So that's one way of looking at these varying acceleration problems. There is another outlook on them. Another way of understanding them is, the integration method. So you can imagine the area under the curve, right? Imagine that we have a little rectangle with a curve, and we have to take segments of rectangles inside, right? And we just approximate. By taking rectangles. I know it's a little off, but that's the area under the curve. This is what's happening here is the acceleration is varying acceleration. So these are tricks to use. Now, like I said, circles is part of this, so let me show you some circular stuff. So in Greece, they had, well, before I get that, let me explain acceleration. I forgot to mention this. Acceleration in the y direction, which we did this in the problem, is always fixed as the acceleration due to gravity. That's what g means, which is about negative 9.8 meters per second squared, right? That is the acceleration due to gravity. It's a constant. It is an approximated value because it changes depending upon position. But let me give you a demonstration of where integrals started from. I feel like that's where we should go, because the idea with this integration is we're trying to go as basic as we can. So I'm going to start with Archimedes. Archimedes started by using what's called the method of exhaustion. So he imagined that if you took a circle with the least sided polygon, which is a triangle, right, got 3 points, you're going to have a separation between the straight line and the curve. And then if you add it with a square, you're going to have the same thing. And then you could have a pentagon, which looks something like this. And then you could have an octagon. This is known as the method of exhaustion. You notice as I add more sides on a polygon, the separation between the circle and the straight side becomes closer and closer together. Archimedes kept doing this until there was 97 sides, and then 97 sides gave us pi, which was about equal to 3.14. It was actually not even an approximation, it was an equal. Pi was equal to 3.14, which gave us 2 decimal values. Now, calculus in Japan, they were obsessed with the circle. They called it the yenri. So they wanted to know, how could they take an area of a circle? Well, they did a crude method. So they would take a circle, slice it in half, and then do little rectangles inside of it, like place little rectangles inside of the circle. Right? And we call this the yenri. That's what this represents. Yenri. And this was by Seki Kawa. Alright, this is calculus in Japan. They wanted to do what was called a yenri. It's the mensuration and measurement of a circle. I am going to show you some vectors. I do have to show you vectors. This is going to be a long episode because there's a lot of vectors that I have to show you. Let's see. I'm going to do this on a separate page. So before we learn how, you know what? Let me show you what vectors are. So imagine you have a straight line, right? Well, actually, let me get started with this stuff. So in the beginning, we talked about motion in the x direction, right? Motion in the y direction. Now we want to know what happens when we have motion in the yx direction. So this is x, this is y, and we call this yx. Now what would happen is we want to take a vector, and we're going to point this vector in the yx direction. So we call this point Q, and we call this terminal. And then we call this back point P, which is initial. So terminal point, initial point. Right? You got, and it's the same thing as final. We just replaced the word final with terminal. But terminal and final represent the same thing. Now, this is where we really got to use averages. We're not really going to worry about instantaneous. Remember the average slope. How would we take the average slope? Or how would we take the average velocity is the question. Remember when we took a graph that was half of a parabola, that we imagined that the other side was the other half of its reflection but we only care about this side. So if we casted a mirror, right, we could create a little reflection on the other side, but we only care about the positive side. This is just imaginary. So remember when we took 2 points, and the points could be anywhere. Let's make the points just random here. So we'll put the points near the end, but not at the end. And then we took a straight line, which gave us an average, and we called this our position, right? And then our velocity. Well, it's the same thing as this. So if we actually replace this with this information here, we would just get something that looks like this. Neglecting the negative side of the graph, I mean, we'd really just have something that looks like this. So you would just replace, instead of using vectors, we'll use this Q, and we'll call this P. And you do use capital Q. Lowercase q is just synonymous, but this is just the same concept. See, all I did was I applied what we learned in the last video, and then I basically just plugged in. I took this and replaced this with this here. This is where we need to get started from because this is the important part. Okay. Now, I'm going to give you a problem. So whenever you take a magnitude of a vector, and we got to get coordinates for me to show you. So I'm going to show you with coordinates. Imagine if we make these, I'd rather just show you numbers. So let's make these coordinates 3, 9. And then we'll call these ones down here, I don't know, 1, 1. Let's do 2, 2. Let's just call these 2, 2. So how would I get the length of a vector, which we call it the magnitude? We want to know what this length is. Now we're not going to, you're going to probably guess that we could take the average. Well, we are going to do that, but we're not exactly going to do this. We're going to do it differently. So to take a length of a vector is this double symbol. It becomes equal to, this is 1. So the formula behind it is, it's Q1 minus P1. So it's going to be 3 minus 2. It's really just doing this. It's really just taking the numbers and doing this. You're subtracting these. So you're 3 minus 2 plus 2 minus 4. It's linear addition. So it's easier for me to put numbers in here. So let's do coordinates, right? We got 3, 9. So we're going to do 3 minus 2 squared plus 9 minus 2 squared. Right? Now 3 minus 2 is going to be, if we break these numbers down, 3 minus 2 is 1 squared, 9 minus 2 is 7 squared. So this is equal to the square root of 1 plus 49. Because 7 times 7 is 49, which you're going to get the square root of 50. That's your exact number. Now, we want a magnitude, so we're going to approximate that. So this, if you break this radical down, you're going to get 5 square root of 2. And then this gives you about you're going to get about 7.07107. And then if it's speed, it's meters per second. Remember in the last video I said speed is the magnitude of velocity? Well, this is exactly how you would talk about speed. It's really hard to mathematically explain speed, but this is how you would find speed. So think of it as the average. I don't like using, well, the instantaneous doesn't really apply to this, but the average works really nicely. Okay, so that's really all you need to know. Other than that, there's just the unit vectors. Oh, if you have a unit vector, I'm going to actually put this up here. So if you have a unit vector, which you call it u hat, I'm using different variables. It'll change as we get along. Well, u hat is equal to velocity over the magnitude of velocity. The double line just means magnitude. I prefer using the double line than using the absolute value, which is just equal to 1 over the square root of velocity. Well, 1 over the magnitude of velocity, I should say, not the square root, times velocity. They're just showing you how a unit vector is always have a length of 1. That's what that 1 means in here. So that is the unit vector. All right, and then another way of understanding the unit vector is a method of trace. So you say I hat is equal to 1, 0. And these brackets are used in vectors. J hat is equal to 0, 1. It's a coordinate system. So because we're dealing with 2 dimensions, I mean, this is all we really need to know. That's it for vectors. This is like vectors in the geometry of space. Let me show you some distance formulas. So if you want to know a distance, right? D is equal to the square root of x final minus x initial squared plus y final minus y initial squared plus z final minus z initial squared. And that's if you need distance. That's what D means, distance. And then equation of a sphere is x final minus x initial squared plus y final minus y initial squared plus z final minus z initial squared is equal to r squared, where r is the radius which is a form of position. All right, and then this is equation of sphere. And the equation of a circle would just be the z being traced out, and you would just have x. If you wanted to do an equation of a circle, it would just be x final minus x initial squared plus y final minus y initial squared is equal to r squared. Adding more variables makes it three-dimensional. Okay, I will check and find out if there's 3D kinematic equation problems. I don't know off the top. I don't even know because I've never done any, but it'd be interesting to find out. All right, and then the last equation. This is nice because we can take a step back from vectors. X final plus x initial, or actually be x initial plus x final, but it doesn't matter. It's commutative if it's addition. X initial plus x final over 2. Y initial plus y final over 2. Z initial plus Z final over 2. Okay. Like in the last episode, I didn't like showing you all these variables, and I don't like tracing things out. So if you, this is the midpoint. This is midpoint formula. Equation of a sphere. Midpoint formula. Okay, if you notice too, there's a similarity between the midpoint formula and the second kinematic equation, where instead we're subtracting the v final minus the v initial. I mean, I know I did it backwards, but you could do it vice versa, final plus the initial. It's commutative if it's addition. And we're talking, and this only works if you're not actually doing linear algebra itself. And like I said before, Calculus 1 is the theme here, but I'm using pieces of Calculus 3 to help explain it. So this is your midpoint formula. And what makes it midpoint is you have an average, so it's the quantity over the quantity. So if it's 3, it'd be over 3, 4 would be over 4, 5 would be over 5. All right, that's about it on vectors. I have to show you vector-valued functions because we have to understand curvature. Because of that, in the circular motion, we have to know about how that works. Other than that, that's it for vectors in the geometry of space. And by the way, this curvature stuff is only part 1 of, the trinity, of the trio. We have to go from there and go further. I'm not going to show you symmetric equations. I don't think they're going to be necessary. The angle between two vectors, we'll save that for when we do the dot product. That actually is the definition of that. Okay, let's see. I had an argument with a student saying that the dot product is not the angle between two vectors, but I'll show you how it is. Like I'll prove it. I'll prove it to you. I'll define it and prove it. It is. Okay, I have to show you vector-valued functions. I know it's ridiculous, but like I said, it's a good idea to take Calculus 3 before you learn this stuff, because I'm basically just throwing down vectors like I expect you to know them, but it's really important on this unit. Like I said, I don't always have to explain them in certain stuff, but we really need them. They're very strong with 2D kinematic equations. Trying to find like acceleration, velocity and acceleration. Okay, this is what we actually need to explain. I'm trying to find a nice diagram. This is really hard. Arc length and curvature. I think this is where I was looking at before. Nope. Bear with me. I have them somewhere. Hold on. Acceleration. Okay. All right. Remember when I said about the vectors, don't worry about them. This is where we're worrying about them. Okay, so this is for non-vector stuff. I like to put it in between to make, kind of like massage out the vectors a little. Okay. So if you have a parabolic function, and I'm going to try my best to try to compare it to a circle. So let's just imagine that we're taking a section of a circle, right? We're just taking like a section of the circle. And we're imagining that it's a stretched out parabola. We're basically just reshaping a piece of the circle. You're going to have a point P and a point Q, right? And these are your points. Okay, and then in between is the change of R. And the change of R, I think, is a vector. Yeah, it is a vector. And then this point traveling in time, well, this one from here to here, we call this the R of t. This is R of t. Can't really see that. This is R of t. And then this point right here is the R of t plus delta t. Okay, that is your velocity vector at time t. So this is your velocity vector. At t, we'll call this. T means time. So you can call this the v of t. And then it changes. So like, if you wanted to do another graph, I guess you could say this. So you take 2 points. This sketch is terrible. You can't really see what I'm trying to show you. Here we go. We want like an average, so we got to get them like off the ends. All right, and then if we wanted to match these points, we would do something like this. It's almost like we're doing a projection. So this is the concept of a velocity vector. Right? It's going to change position, like depending where it's going. It's going to change. And then you're going to get something that looks like this. So if I wanted to do a projection, right? It would create like a circular sort of path. Like a little, it almost will create like a little, like a slice, like a surface. It's almost like we're looking at a surface of some shape. All right, this is a little weird. It's confusing. All right, that is the velocity vector. Just really worry about this part. Don't worry about this. I was just trying to go like above and beyond there. I made it confusing. So that's the velocity vector. Trying to see if there's an acceleration vector. Guess not. I'm going to show you the summary of, or I'm going to show you like the whole, everything you need to know for arc length, you don't even need to worry about. All right. All right, so, like I said, this is like, I don't want to do vector boot camp, but this has to be vector boot camp. There's no other way to explain it. I'd rather go on and on and on with vectors, so that way you're well equipped. So if you took the r of t, it's equal to the x of ti plus the y of tj plus the z of t. Oh, it's just two variables. Okay. X of ti plus the y of tj. Basically, the way this works is imagine that the z is traced out. We set the z equal to 0. We got rid of the z. But that's if you have two variables. But if you're doing 3, you could say the r of t is equal. Well, basically, if it's 3, you could just say the r of t is equal to the x of ti plus the y of r of t is equal to the x of ti plus the y of tj plus the z of tk. Just add in another variable. All right, and then remember that velocity, the v of t, is equal to the first derivative of position. This is just a different notation. This is the same thing as what we said over here. It's just a different notation. It's the same thing that velocity, right? Instantaneous velocity is the first derivative of position with respect to time. This is the same thing. It's just in different notation. Velocity of time is, this is what they call an Euler expression. The velocity of time is equal to the first derivative of position with respect to time. It's just an Euler notation or a Newtonian notation. Newton and Euler had this little parenthesis rule. And that's if you wanted the velocity vector. Now, if you want speed, you just simply take the magnitude. Right? It's just magnitude, really. I mean, they just do ds dt instead of dx dt, but it's the same thing. I mean, ds dt and dx dt, they mean the same thing. Let's call this dx dt. Okay. So that's if you have speed. And then if you have acceleration vector, right, the a of t, we're good with that. It's just the second derivative of position with respect to time. Remember I said that velocity is the first derivative of position, acceleration is the second derivative of position. And then you got to also remember that this becomes equal to, and this is if we're doing tangential velocity acceleration. This is actually good for when we get to non-uniform circular motion. And these little bases are vectors as well. What T stands for is tangential, and N stands for normal. So it seems like tangential is the tangency. It's basically like when we take the slope of a curve, that's our tangency. I'm trying to find those sketches I made. So tangency is, I'll show you what tangency is again. I can't find a good explanation. So tangency is if we take a curve and we want a point, right? It could be instantaneous, it could be anything. It's the straight line of the curve at a point. That is what the tangency is. The normal vector is the vector that's going to point orthogonally out. So that is our normal vector. And what makes it normal is the fact that it's 90 degrees. The vector between here and here is 90 degrees. That's basically what tangent vector means. This is tangent and that's normal. So you could think this is t and you could think this is n. That's where these bases come in. It's kind of cool how we're not avoiding bases this time, but we're using them with vectors. It's kind of neat. Okay, that's the acceleration vector, which you're going to say that this is equal to d squared s. We're going to use x. I'm not even going to use s. D squared x dt squared on the tangent of t. Oops, there's a plus here. D squared x dt squared tangent of t plus k. K just stands for curvature. This is curvature. Curvature of dx dt squared, and that's the normal of time. All this is with respect to time. It's kind of like how we looked at these original kinematic equations. We talked about time, but we really didn't express it. Here we're doing that. I mean, it's a neat comparison. So that is k is curvature, and this is speed. This dx dt is speed. Unit tangent vector do we need? I'm going to do unit vectors. We don't need to know components of acceleration. That's ridiculous because then I have to show you the dot product. We're not even going to do the dot product. We'll save that for the dot product stuff. Formulas for curvature in the plane, we don't need those. Formulas for curvature in the plane or in space, we don't need. One more I'm going to mention, though, the unit vectors. So if you take the tangent of t, this is equal to r prime of t divided by the magnitude of r prime of t. Prime means derivative. This is first derivative. And then the normal of t is equal to tangent, hold on, let me write this below. Normal of t is equal to tangent prime of t over the magnitude of tangent prime of t. Okay, this is ridiculous, isn't it? I had to show you all this math, but it's the same pattern if you can pick it up. It's just the notation changes. So like we're changing variables here. I mean, we're constantly changing variables. And I'll tell you an interesting fact. There's going to be a bonus lecture about change of variables. And actually, it's not change of variables. It's going to be an extension of Newtonian Mechanics at the very end. And it's going to be quite interesting. I mean, this stuff is really cool. But anyhow, if you're ever not sure about this, just look it up. It's called vector valued functions. This is your notation. Okay. Sorry if this is complicated. I don't like the way they explain how physics defines, like, they don't really go in depth with curvature. So I figure it's important to cover that first. And this is, like I said, a long lecture. Okay, we're going to cover now motion in 2 or 3 dimensions. We're ready to do this. We are ready to do this. Okay. Don't worry about if the acceleration is speeding up or speeding down. Let's just stick with normal acceleration. We're not going to vary the acceleration. And the reason why, you know what, I'm going to show you. Because, like I said, the whole thing with this is circles. I'm going to just show you. It's not that bad, trust me. This stuff... Sorry, the thing fell. This is insane. All right. I think we're okay. All right. As far as this acceleration goes, and like I said, our whole theme with this is we want to deal with circles, right? We want to worry about circles. So I'm going to show you what happens when the acceleration speeds up and when it slows down. I'm going to show you that. And trust me, this is easier than what I just showed you earlier. This is actually not as bad. What I showed you before was brutal. All right, so still here, I'm just writing out the problem. Basically, what I was trying to show you in a very straightforward way. Actually, this is a terrible graph. I gotta make it normal. What was I trying to show you with all that crazy math? Okay. What I was trying to show you, this is a section of a circle, right? I showed you the circle. This is a section of the circle. This is like, and you can think of this as the sun, right? This is a section of the sun. And like I said on the video, we're going to start from a star to a frozen star. So when you take the first derivative, you have velocity. And remember that the acceleration is normal to velocity. That's basically what I was saying on this sheet. I mean, here we call velocity the tangent, right? Called it the tangent vector. And then acceleration, we called it the normal vector. So that's basically what we were doing. We were just interpreting that to, it's just change of variables. We were basically, it's kind of like a transformation the way I'm setting this up. It's kind of cool. But we were just, I'm spicing it up a little bit. Okay. I'm going to show you what happens when you increase the acceleration and then when you decrease it. Instead of just going back and forth, I'm going to show you what happens when you increase it and when you decrease it. The reason why I'm doing this is because it helps with the, like I said, I want to make integration count as much as we're doing derivatives, but I don't want to have to explain it with integrals. So my best method is that I explain it using geometric tactics. Okay. Okay, so here is the curve, right? Here is the curve. The velocity vector stays the same, if you notice. Now, the acceleration changes. You could call this your normal vector, right? We can call this our normal vector. When we speed up, if we're driving on a curve or we're running on a curve, the acceleration is going to go upward. Now, if we slow down, it's going to go downward. This shows you like the geometric change of the circle. You can almost imagine like you're orbiting around the sun. Other than that, I guess I could show you planetary orbits. Hold on. I'm trying to get organized here. I'm going to save it for the end. Okay. So, let me explain projectile motion really quick. I know this is crazy. This isn't, trust me, a lot of this is just geometry. Most of what I have to show you is geometry. I mean, the beginning is rough. The beginning is rough and tough. But this is just geometry. Now, we call this the y. Call this the x, right? And that, because we no longer care about the y or the x. We want to care about the yx. If I have projectile motion, that's parabolic. It's like a negative of a parabola. So in projectile motion, we always have the origin, initial velocity, and then this goes here. First velocity, second velocity. We call this three velocity. Now I got to show you components. V sub x, V sub y. Fix that. V sub y. V sub x. V sub y. Notice when it reaches straight, it has no components. It only has components if it's in an angle. If it's 90 degrees, no components needed. Well, 90 or 180 degrees. And then this is V sub x, V sub y. Okay, so that is if you have projectile motion, and you can imagine that this is being traced to this. This is like the 1D kinematic projection in the x direction of this problem. Isn't that cool? And then if you wanted to look at it this way, you could have all right, that is your y projection. So you got a y motion projection, and a vertical projection and a horizontal projection, which together gives you, this is if it's traced out, it gives you this whole parabolic segment. Okay, that's it for the theory. We're going to do a problem. Before I continue, we are going to do motion in a circle. I'll explain it in the end. Because the way I want to do it is we're going to do relative velocity. I might even do a problem with it. Maybe not. I want to do a problem now. Before we go into 3.5. Okay, section, the acceleration vector. A jet plane is flying at a constant altitude at time t is equal to 1 is equal at time t1 is equal to 0. It has components of velocity 90 meters per second in the x direction. Y is 110 meters per second. At time t2 30 seconds, the components are negative 170 meters per second, 40 meters per second. Sketch the velocity vectors at t1, t2. How do these two vectors differ. For this time interval, calculate the components of the average acceleration and the magnitude and direction of the average acceleration. Okay. Here is my, hold on. Still here. All right. Still here, guys. I'm just trying to set this up. Okay. All right. So velocity average is R final minus R initial over T final minus T initial. Okay, so that's 14 centimeter I hat plus 10 centimeter J hat. This is just 4 centimeter I hat. And now I want to take the average velocity. All right, so you get 5 centimeters per second I hat plus 5 centimeters per second J hat. That's the I and J. Now I want to know the magnitude. So I get 7.1 meters per second. And then we want to know the angle between the two vectors. I didn't really show you that part because it's very straightforward. So you get the arctan of 5 over 5 is equal to 45 degrees, and this is 5 squared plus 5 squared. All right, and this is all they really need is magnitude and direction. And that's part A. And B is it's just the velocity vector. It's equal to, well, we're going to use R now. All right, so you get 5t I hat plus 5t j hat. All right, and then because there's no t, this is 0, basically what they're showing you. So v of t equal to 0 is equal to all right, this one is, I take it back. This is your answer, 5t I hat plus 5j hat. V of t equal to 0 is 5 centimeters per second j hat. And then just the instantaneous velocity is equal to 5 centimeters per second. Which there's no t. Actually, I was correct. There's no t, so this one would be 0. And then alpha is equal to the arctan of 5 over 0, which then is defined as, or equal to, this is the arctan, because 5 over 0 is infinity. The arctan of infinity, which is equal to 90 degrees. Because 5 divided by 0 is infinity. 0 over any number is 0. 5 any integer divided by 0 is infinity. What happens with that phenomenon is it blows up. Something you would see in a convergence test with series. You see that when you take calculus too. Okay. That is part B. All right, so I think I showed you if it's t is equal to 1, it's the same answer. You're going to get 45 degrees. So this is your I'm still here, just... Alright, let me do this one. Alright, so we do V, velocity, the velocity vector of t is equal to 2, is equal to 5 times 2, I hat plus 5 j hat. And then if you wanted to find the magnitude, which is just the magnitude of V, is equal to 10 squared plus 5 squared, which is then equal to 11.2. I'm going to get an approximation, 11.2 centimeters per second. And then alpha is equal to the arctan. So this is your magnitude. And then this is 11.2 meters per second. Alpha is equal to the arctan of 5 over 10, which you know that's 1/2, right? This is 1, this is 2. You simplify it, which is going to be equal to, or about, 26.6 degrees. So this is your magnitude and direction. 11.2 centimeters per second, 26.6 degrees. Magnitude and direction. Okay. Remember, the magnitude is the length of a vector. The direction is, magnitude tells us how long the vector is. Direction tells us where is it pointing at. Now, if you notice that this is what they call a reference angle, there's this method of finding proper angles. I could show you that if you want, but that might be too much. Just look it up. This is what they call a reference angle. So this is defined as theta reference. I'll show you what the heck. So if you're in quadrant 1, quadrant 2, quadrant 3, quadrant 4, if you're with respect to x, so if the angle comes from this direction, the problem with physics is they don't really show you this. Theta is equal to theta. Theta is equal to 90 degrees minus, actually, theta is equal to 180 minus phi. And then here you have theta is equal to 180 plus phi. And that's if you're over here. This works if you're over here. And then if you're in quadrant 4, you say that theta is equal to 360 minus phi. Phi is just the angle in between. So this is how you find proper angles. Now, if you're going from the y direction, right? You're going from the y direction, you're going to do it a little differently. Like I said, we're going to do circles in this episode, so that's the big thing here. Okay, y direction. Theta is equal to 90 minus phi. Right? Theta is 90 minus phi. The y direction, yeah. And then theta is equal to 100. Are we 100? No, theta is equal to 90 plus phi. And then theta is equal to, because we're coming in from the y direction, right? It's got to be the opposite, so it's 270 minus phi. Theta is equal to 270 plus phi. Okay, this is how you would find proper angles. Now this is if this is respect to x, and then this is respect to y. Okay, so one shows you if you're coming from the x-axis, and the other one shows you if you're coming from the y-axis, or you can think of it as a line. That is, like I said, this episode is full of circles. I apologize if I had to show you that. Other than that, we did good. Oh, I didn't do part C. Forgot part C with that. I just thought I'd show you the reference angle and the proper angle. I always get off on a tangent with these. Okay. So part C, we're pretty much there. We just have to make a graph. Okay. We're like 90% done. Part C. Okay, you got y, and then you have x. If you want, we could call them vectors. I'm not. Position, right? So this one's 4. And then we said t is equal to 0. This is velocity. And then we'll make this 8. Actually, we'll make this 7. This has to be 7. This is 7. Right? It's 7. Or about 6.25 to be exact. We'll make this 6.25. And then you're going to have v t is equal to 1 second. And then here, we're making this 14 now. 14 v t is equal to 2 seconds. Okay, that's it for this problem. Just shows you how the position is always the velocity is always trying to stay close to the curve. If you have constant acceleration, remember the acceleration, you always have a normal vector. Right? It always points this way. It's kind of what I showed you. Okay, that is it for, that's it for this stuff, for 2D, I think. Well, we're still got a little ways to go. All right. Oh, I want to show you something cool. So, if you think about our planet, right? You're going to have a moon that's orbiting around our planet. And it kind of follows circular motion. Another way to think about it is when the sun, like we'll call this Earth, and then we'll call this the moon. Actually, we're not going to call this moon. This is sun. Right? When you have the sun, you're going to have all these little, I'm going to do it on another page. So if you're going to have the sun, right? You're going to have all these little rings that go around them. And these rings are perfect circles. These orbits, these planetary orbits. 1, 2, 3, 4, 5, 6. We'll do 7. So you could have like Mars, Venus, right? Earth, Jupiter, and Saturn, right? Oh, no, is it Venus? No, Venus, no, Mercury, Venus. Sorry, I'm just tired. Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Let's just stop there, because the reason why I'm going to stop here is because of the fact that back in the day, in the naked eye, they only saw like 7 planets. I don't feel like doing 9 rings. But the idea is, throughout the naked eye, the farthest planet in space you can find is Saturn, which Saturn looks more like this. It's just something cool to show you. They call it the Roy, no, not the Roy G. Biv, Mr. Vemg Sum or something like that. There's an acronym to remember the planets. So this shows you that in the ancient times, like Copernicus believed that the orbits around the sun had perfect circular paths. They were just circles. They had symmetry. And what they mean by symmetry is whenever you have a circle, you could slice it this way, you can slice it this way, you can slice it on infinitely. I know this is making you hungry. You're probably thinking of pizza right now, but it's just the idea that I could keep slicing it no matter an infinite amount of times, and I'm going to have symmetry consistently. And if you ever look at a focal point of a circle, it's always going to be in the center. So that's why they believe that everything was symmetrical. I mean, this is an example of symmetry. Other than that, I mean, this is interesting. So I just thought I'd share that out about the sun. Copernicus believed that the planets have perfect circular orbits, but then Kepler, in Kepler's laws, he later described that they do not travel in perfect circles, they travel in ellipses. I just thought that was neat to show you because it applies with circular motion. Other than that, let's explain relative velocity, and then I will close this up. Okay. So, relative velocity works in relation with Einstein's special theory of relativity, which lacks, which actually does lack acceleration. And that's why I was trying to give you like the clue, like in the beginning when we did 1D and 2, when we did 1D, well, the end of 1D and when we got in the beginning, especially when we got in the beginning of 2D, is that that's how it behaves. So let me show you how. And it obeys classical mechanics, which is incredible. Okay, so acceleration. So I'm going to show you the differential part. So you could have x of p over a plus x of p over b plus x, oh wait, I wrote this wrong. X of p over a is equal to x of p over b plus x of b over a. Not going to really do a problem because these are going to take so long. You can imagine this as a derivative, so you could say dx of p over a. Just think of this as a notation. Don't really worry about this as a derivative. Dx of p over a dt is equal to dx of p over b dt plus dx of b over a dt. Okay. And that's relative velocity along a line. All right. And then if you wanted to do relative velocity in space, you could then say r of p over a is equal to r, position of p over a is equal to position of p over b plus position of b over a. Okay. That is about it. I'm not going to do a problem. Like, we did problems with the plane. I had to find the best problem there was. Alright, I feel like if I do this vector stuff, I'm just going to repeat everything I showed you. Kind of showed you in the beginning. I'm not going to do it. Just remember, though, that if you have the position, that's just equal to the x of I hat plus the y of j hat plus the z of k hat. The changes are equal to the change of position over the change of time. It's pretty much this. It's pretty much what I just showed you in the beginning. And then if you wanted to take components, like let's say you took components of acceleration, that's equal to, you just do a little component at the bottom. So a sub x is equal to dv sub x dt, a sub y is equal to dv sub y dt. This is just an extension of what we learned in 1D kinematic equations. A sub z, dv sub z dt. So that's about it. Projectile motion. I guess I'm going to have to show you the equations for them. Okay. So projectile motion, right? You have x is equal to v initial cos initial t. So that's x is equal to v initial cos of acceleration initial t. Y is equal to v initial, well, v initial sine a initial t. And then minus 1/2 gt squared. And this is if you have constant acceleration. Of course, they say no air resistance. It's the same game. Constant acceleration. V sub x is equal to v initial cos of acceleration initial. And then v sub y is equal to v initial sine of a initial minus gt. And that's acceleration. Now, what's interesting is nothing really happens when you're in the x direction. Like, it's kind of the same. Like, you have a t, but you don't for the y. These kind of, like, work similarly to these constant kinematic equations. Where is that sheet? So you could see the resemblance here. I mean, you could see how this first kinematic equation is just like this first one here with the position. You can see a little similarity here if you look at these ones, actually. So v initial cos alpha initial t. The same rules apply. You're going to have no, I guess you have no final speed, right? No final speed. I mean, if you think about it, it's just the initial. They all have no final speed, actually. Other than that, they do have a position. They do have an acceleration. I guess the same thing goes here. No final speed, right? No final speed. We could say this. And then if we look at the third one, we're going to say it has no time, right? No time. No time. And no position or distance, right? No distance, because there's no x. And then the other one, we could say it has no, because it has to have no something, no distance. Okay. No final speed, no final speed, no time, and no distance, and just no distance. All right, so this is beyond Galileo and Newton, as you can see. Now, I do have to show you a couple of things. They're really quick. If you're going to have centripetal acceleration, right, which you can call it radial acceleration, I don't know how to, I'll just keep it RAD, is equal to v squared over r. And then you're going to have, you could say that this is equal to 4 pi. Actually, I'll also say this. So the radial acceleration could be equal to 4 pi squared r over period squared. Now, I didn't explain what period was. This is not tangent. This is period. Period is an inverse of frequency. So it really, period and time are kind of the same thing. It's how much revolutions per minute is a period, so how many RPMs. So like if you turn a record and it does like 33 RPM, 45 RPM, 78 RPM, it's how many RPMs are for, it's revolutions per minute, which is basically a period, and that counts as a time. All right, so that is period. Now, the way this circular motion works is this is uniform circular motion. This is uniform. It's very important that you understand that. Uniform circular motion. Right? And it's the same thing. And what makes it uniform is that the acceleration vector is constantly going in. This is what they know as the radial acceleration. And then this is the velocity vector. Right? And then I mean, technically this is supposed to be the same length, but that's okay. I mean, it's close enough. All right, that is uniform circular motion. What makes it uniform is that, if you notice, the radial acceleration is constantly parallel with the normal vector. This is where I was showing you the normal vector. It's kind of like this problem. I mean, if the velocity was decreasing, I mean, if the acceleration was changing, right, we would say that it would increase, but we'll just leave it like that for now. Other than that, I'm going to show you relative velocity along the line. So relative velocity is the velocity of P over A is equal to the velocity of P over B plus the velocity of B over A. And it lacks acceleration. So this is everything that you need to understand. Other than that, the stuff that I showed you, all this is not really going to matter for next week, but it's very important to understand the foundation of physics, and I apologize that this video is so long. It's just that I had to show you vectors. So, I just hope you enjoy it. Thank you.